Welcome to the third Geometry Intermediate lecture. Today what we'll be doing is circle geometry. Okay, so there are 7 theorems in circle geometry that you need to know, and I will be going over them in some detail. So the first theorem, these are normally done in grade 11 at school, theorem 1. So what we have is we have a circle, and we have a chord AB. We have the center of the circle, call it O, and we drop a perpendicular from, what we'll do is we'll connect the midpoint of AB, so connect the midpoint of AB with the, and then what we want to show is that when we connect the midpoint, the center of the circle with the midpoint of the chord, it is perpendicular onto the chord. So given a circle with center O, and chord AB with midpoint D, not with midpoint D, with D on AB. So given a circle with center O and chord AB with D on AB, if AD equals DB, then OD is perpendicular on AB. So this is the first theorem for circle geometry. So we are given a circle with center O and the chord AB. If we connect the center of the circle to the midpoint of the chord, it is actually perpendicular on the chord. So if AD is equal to DB, then OD is perpendicular on AB. Okay, now we need to prove this. So I'm going to write out this proof properly so that you can also get a sense of how to actually write down the proof very nicely. Okay, so here's the proof. Okay, proof. Okay, so our first part of the proof will be a construction. This is different than the ruler and the compass construction. This means adding things to a sketch. So you get 2 different types of constructions. One is making constructions by ruler and compass constructions. Another is adding things to sketches. So by this construction, I mean adding things to sketches. So in this case, draw OA, OB. So we draw in OA, OB. Okay, so this is part of the first one of the proof. We just say what we do on the sketch. Okay, then. And I'm going to write down this congruency proof. You might now notice what's going on. In the 2 triangles AOD and BOD, we have that OD is common, OA and OB are radii, so they're equal, and AD and DB are equal. So I'm going to do this congruency proof properly, so that you can also see a nice proper congruency proof. In triangle AOD and triangle BOD. Also, the other thing about congruency, please keep and similarity also, please keep the angles corresponding. So angle A corresponds to angle B, angle D corresponds to itself, and angle O corresponds to itself. So please also keep the angles in the correct order. The order of these angles are very important that you list them in. In triangle AOD and BOD, 1, OD common, is common. 2, AD equals dB, or AD equals BD, and this reason here is given. And then 3, OA equals OB, and the reason here is radii. And then we have a conclusion. Hence, triangle AOD is congruent to triangle BOD. The reason here being side, side, side. Okay, and then once we have that, they're congruent by side, side, side. That means these two angles are equal, and since they're equal and sum to 180 degrees, each of them is 90 degrees. So we can make the final conclusion that we thus angle OAD equals angle, ODA. ODA equals 90, well, equals ODB equals 90. So ODA equals ODB equals 90, implying that OD is perpendicular onto AB, which is what we wanted to show. Okay, this is the first of 7 theorems. Okay, so OA equals OB equal radii. So a good construction to do when you have circles is drawing in the radii is usually a good idea. Okay, so that is the first circle geometry theorem. The second geometry theorem, I'm going to just make some changes on the sketch. I'm going to make some changes on here. I'm not going to redo it. Okay, so the second geometry theorem, so theorem 2. Okay, so what we are given this time is we given the following. This time around, we are given a circle with center O, so more or less same setup, and chord AB, and D on AB, but we are not given that if AD is equal to DB. What we're given this time around is if OD is perpendicular on AB. So we're given the opposite, basically. And then we have to prove the opposite, which is that AD equals to BD. Okay. Like this more, AD equals to DB. So, the proof remains more or less the same. Construction again, start by drawing in the radii. So that remains the same, drawing OA and OB. In triangle AOD, and we're going to use the same two triangles for congruency. OD is still common, so that is still fine. This time around, we don't have that AD is equal to BD given. So we don't have this. We still have that OA equals OB radii, so that remains. But this second reason changes. The second reason now changes to, because we are given that OD is perpendicular to AB, these two angles are equal. So we are, this time the reason is that angle ODA equals angle ODB. And this is given, so the reason is still given. Hence, the two triangles are still congruent. This time around, it's not side, side, side though. This time around, it is 90 degrees This time around, it's 90 degrees, hypotenuse and side. 90 degrees hypotenuse and side. And thus, therefore, changes because, okay, now it's just the direct conclusion. AD is equal to BD here. So we just directly now conclude, because the two triangles are congruent, that AD equals to BD. Okay, and this is the second theorem. So it's basically the converse of the first theorem. Okay, then following from the first and the second theorem, there's a corollary. And the corollary is that the center of a circle is on the perpendicular bisector of the chord. So the corollary following from theorem 1 and 2, so corollary is like a small result that follows, or a result that follows directly from a theorem. And it says that the center of the circle is on the perpendicular bisector of a chord. So the center of the circle is on the perpendicular bisector of the chord. So if you perpendicular bisect the chord of a circle, the center must be on that line. And then how you can find the center of the circle, as I said in the construction, you just need two of these chords and perpendicular bisect two of these chords, and the intersection point will therefore be the center of the circle, because the center of the circle must be on both perpendicular bisectors, and hence it's the place where those perpendicular bisectors intersect. Okay, so that's the first two theorems and the corollary on the theorem. Okay, now for theorem 3. Theorem 3 is very, very important. It also has 3 corollaries. Okay, so let's change it to theorem 3. Okay, so theorem 3, let's see what changes. We have a circle with center O. Okay. Given a circle with center O and chord AB, we are still given chord AB. Yeah, I can draw in chord AB. We don't have with D on AB and this. These all come out. And we take a point C on the circumference. Okay, chord AB and C on circumference. Then what we have is that the angle with C on the same side as O, from AB. Okay, so C is on this side of AB. Then what we have is that angle. Then angle AOB. Make this larger. Then angle AOB is equal to twice angle ACB. So the angle at the center of the circle is twice the angle at the circumference of the circle. So if you draw in this over here, the angle at the center of the circle is twice the angle at the circumference of the circle. Okay. So what we want to show is that the angle at AOB is twice the angle ACB. Okay, so we need to now prove this. Where do we start the proof? Well, similarly to the previous one, we draw in a radius. The only missing radius in this case is CO. Except what I'm going to do is I'm going to actually extend CO a bit. I'm going to extend CO to actually a point on D. So construction this time around. Draw COD. Over here. Okay. And the congruency proofs falls away. This has nothing to do with congruency. That all can come out. Okay. Now notice that OC equals OA, so OAC is an isosceles triangle, and similarly OCB is an isosceles triangle. So the angle OAC and the angle OCA are equal, and the angle OCB and OBC are equal. So what we have is we have that angle. Okay, so the angle AOD. So let's start with angle D. So the angle D. The angle AOD. Actually, I'm going to split them up directly. The angle AOB equals to the angle AOD plus the angle DOB. So the angle AOB is equal to the angle AOB is equal to the angle AOD plus the angle DOB. And then the angle AOD AOD. This is the exterior angle of triangle OAC. So it's the sum of the opposite two interior angles, these two angles. So AOD can be changed to this is equal to OAC plus OCA. And then the other one would be on this side by similarity OBC plus angle OCB. Then angle OAC is the same as angle OCA. So we can change OAC to OCA plus OCA, keep the second one the same. And this OBC can be changed to OCB. So this changed to OCB plus OCB. Now we have OCA and OCA, that's two of them, and we have two, so this is equal to twice OCA plus twice OCB. So this is twice OCA plus OCB, but OCA plus OCB is just ACB. So this is just equal to twice angle ACB. Yeah. This is so OCA and OCB just sums to ACB. So this is twice angle ACB. And now we have that the angle at the center of the circle is equal to twice the angle at the circumference of the circle. Okay. This is the third theorem. It has three corollaries. Corollaries that follows basically immediately from the proof of this theorem. The first corollary says that the angle at the center of the angle in a semicircle is 90 degrees. That's the first corollary. I'm actually going to list the corollaries here at the top. Okay, so this actually is supposed to be below, but I don't have space on the board. Actually, what I can do, no, let me just wipe the proof out. So that's the proof. Let me wipe the proof out, and then I'll put the corollaries here at the bottom. Okay. The three corollaries. The first corollary, angle in semicircle is 90 degrees. The second corollary says that angles subtended by a chord on the same side of the chord are equal. Angles subtended by chord at circumference by chord angles subtended at circumference on same side of chord are equal. And then the third corollary, basically the same as the second corollary, it said that angles subtended by equal chords. Angles subtended by equal chords on circumference are equal. Okay. Angles subtended by equal chords on. Okay, so to just go over the proofs of these three corollaries. Okay, so angle in a semicircle. So I'm going to just do, I'm keeping this sketch and just doing a rough sketch over here. So if you have a semicircle, so you basically have the diameter, angle in a semicircle. Well, we said that the angle at the circumference subtended by the chord is double the angle at the center of the circle. Oh, sorry, the angle at the center of the circle is double the angle at the circumference of the circle. Well, if it's a semicircle, it means that this length here is the diameter. It means that the angle at the center of the circle is 180 degrees. which means that half 180 degrees is 90, so that angle therefore is 90. Because the angle here is 180 degrees. And that is why the angle in the semicircle is 90 degrees. It is half the angle in the center of the circle, which is 180 degrees. Okay. If we have the different sketch. Okay, angles obtained by the same chord are equal. So these angles here, this angle here is equal to this angle here, because both of them are half the angle at the center of the circle. So if you were to draw in the center of the circle and connect it, this angle is half the angle there, this angle is half the angle there, so they must be equal to one another. And for any angle you form, basically, they're always going to be half the angle at the center of the circle. And the angle at the center of the circle is fixed by this chord. And then, for the same reason, if you take equal chords, so not necessarily the same chord, but equal chords, if you take a chord over here and you take a chord over here, and you take the center of the circle, because the radii are equal to each other, there and there, you have congruent triangles because of side equal length chords. Equal length chords means the two triangles are congruent to each other, means this angle equals this angle, meaning that the angles obtained the circumference of a circle, the angles obtained on the circumference of a circle by this chord is half the angle at this center of the circle, but that's equal to the angle here, which is double the angle of any angles obtained by this chord on the circumference of the circle. And that is why the third corollary then also follows. You can basically just rotate the one triangle onto the other triangle if you want. Okay, that is the third theorem with its three corollaries. Okay, next up, definition. Okay. Definition. Cyclic quadrilateral. Cyclic means circle, quad means four, lateral means sides. Now note that given any 3 points or a triangle, you can always draw a circle through the 3 points. So given any 3 points not in a straight line, you can draw draw a circle through those 3 points. So any triangle can be circumscribed by a circle. However, if you have 4 points, that is not necessarily true. If you take these 4 points, for instance, you can't circumscribe a circle around these 4 points. So if you take, for instance, a quadrilateral, say we take this as a quadrilateral. So we take this as our quadrilateral over here. We cannot circumscribe a circle around this quadrilateral. So the special cases where you have a quadrilateral, a four-sided figure that can be circumscribed by a circle, is called a cyclic quadrilateral. Note all triangles are cyclic. Okay. So the next theorem, theorem 4, deals actually with cyclic quadrilaterals. Okay. Theorem 4. Given the cyclic quadrilateral, A, B, C, D, we have angle A plus angle C equals 180 degrees. So the opposite angles in cyclic quadrilateral sums to 180 degrees. Okay. Okay, so you have a cyclic quadrilateral circle, and you have a quadrilateral inscribed in here. Okay. let the center of the circle be about here. We want to show that angle A, B, C, D. Okay, the proof of this. Proof. Okay. Construction. Draw. Okay, now first center of circle. Call it O. And then draw OD, OB. So you draw in OD and you draw in OB. Okay. Then chord DB subtends the angle at the center of the circle. That is twice the angle at the circumference of the circle. So call this O1 and call this O2. O1 and this 2. Okay, just call that O1 and that O2. So angle O1 is equal to twice angle angle O2. Angle O2 is equal to twice angle DAB, and angle O1 is equal to twice angle. So on the other side, DB the angle at C will be half the angle at O1. So twice angle DCB. If we then sum these up, O1 plus O2 is equal to twice DCB plus twice DAB. But O1 plus O2 is 360 degrees. And you have twice there, so what happens is, yeah, so 360 degrees equals twice angle A, angle C plus angle A. So angle A plus angle C equals 180 degrees. Okay, so the opposite angles in the cyclic quadrilateral sums to 180 degrees. Okay, that is the fourth theorem.